Alright, this is a redo of problem number 10 with a little change in the way we handle the algebra related to rational exponents. Alright, for A, we want to find the coordinates of all points at which the tangent is a horizontal line. So we need the first derivative, set it equal to 0, and solve for x. And the first derivative then is 4/3 x to the 1/3 plus 4/3 x to the negative 2/3. Set that equal to 0. Now it's easiest to solve this, and the proper way to solve this would be to factor out the greatest common factor, the same way we would do with a polynomial. And that greatest common factor would be 4/3 x to the negative 2/3. And when I factor that out, I get x to the 3/3 for the first time. Since we multiply two numbers with the same base, we add their exponents. Negative 2/3 plus 3/3 equals 1/3. But x to the 3/3 is just 1, so I'm going to leave that as it is. That's just x. And then I have plus 1 on the other for the other term. And so I have 4/3 x to the negative 2/3 times x plus 1. That equals 0 only when x is equal to negative 1. And the question, that's the only place where it's equal to 0. But the question asks for coordinates, so I'm going to plug that back into the original function. And I have negative 1 to the 4/3. I need the cube root of negative 1, which is negative 1 raised to the 4th power. It's going to come out to be positive 1. Again, x to the 1/3 is going to be negative 1 times 4 would be negative 4. So I have 1 minus 4, or negative 3 for the y value. Alright, next we want to find out the coordinates of all points at which the tangent to the curve is a vertical line. And the vertical tangent will occur whenever the denominator is equal to 0. And from our factored expression, we can see that the denominator will be 0 at x equals 0. And we should note that both of those, negative 1 and x equals 0, are critical values of f of x. By plugging in x equals 0 into the original function, we get y equals 0 as well. So we're done with A and B. We're looking for the absolute max and absolute min to occur, or where they occur. And we know that they will always occur, absolute min and max will always occur at either critical values or endpoints. We have the two critical values, which are x is negative 1, x is 0, and the endpoints would be x is negative 8 and x equals 8. So we need to evaluate the original function at each of those points. Again, the telltale signs are that you're asked for absolute min and max, you're given a continuous function on a closed interval, and we already know f of negative 1, that's negative 3, and f of 0 is 0. F of negative 8. So we have the cube root of negative 8, which is negative 2, raised to the 4th power, which is positive 16. Then we have cube root of negative 8 again, which is negative 2 times 4 is negative 8. So we have 16 minus 8, which is positive 8. For the second one, we're still going to get 16, and 16 for the first term, and we're going to get 8 for the second term, only both of them will be positive, and we'll end up with 24. And so from this we can see that the absolute minimum is at x equals negative 1, comma negative 3, and the absolute maximum is at 8, comma 24. Alright, so we're done with C. We need to find out on what values of x this function is concave down. And for that we need the second derivative. We want to find out when the second derivative is negative. Well, the second derivative is 4/9 x to the negative 2/3 minus 8/9 x to the negative 5/3. And we're going to factor out, set it equal to 0, factor out the greatest common factor, which is 4/9 x to the negative 5/3. And for the same reasons as before, that's going to leave me x to the 3/3, which I'll just call x now, and minus 2 there, because 2 times 4/9 is going to give me 8/9. Alright, so that will be 0 when x is equal to 2, but it doesn't exist when x is equal to 0. So these are like critical numbers. With second derivatives and points of inflections, we don't call those critical values anymore. They are now potential points of inflection, or candidates for points of inflection. So we set up the sign chart, select some test values, and we're going to plug them back into the second derivative because we want to find out when the second derivative is negative to find when it's concave down.